Hello everybody, this set of notes is going to go over properties and changes and types of matter. We're going to break the properties of matter into two big categories. The first category is extensive properties, and the second category is going to be intensive properties. Extensive properties depend on the amount of matter that is present. It's going to change based on the quantity of substance that you have. So for example, volume, mass, how much energy it contains, those are all things that will change based on how many molecules you have. So for example, if you have a teaspoon of water versus a cup of water, sure, it's still H2O molecules, but the volume is different. Intensive properties only depend on the type of matter that you have. The quantity does not change it. So for example, the temperature at which it melts, the temperature at which it boils, or what its density is, those are all things that only depend on which type of molecule you have. For example, water will always boil at 100 Celsius. If you have a cup of water, or you have a whole pot to make spaghetti or something on the stove, it will still boil at 100 degrees Celsius. So the quantity is not going to change it. It may take longer to boil, but it will still boil at the same temperature because it is still H2O molecules. So we can kind of take our two categories of matter and kind of look at what we're talking about and decide, does it fit into an extensive property or does it fit into an intensive property? So look at these examples for a minute. Which of the following is an extensive property? We have one choice is that it's a solid at 25 degrees. Choice B, it has a density of 1.38 grams per centimeters cubed. C, it melts at 62 degrees. D, it has a volume of 0.52 centimeters cubed. And E, it is shiny. When I look at these, I'm going to be trying to find which of these has to do with the quantity. Extensive has to do with the amount. Well, solid's going to be a solid even if I have a little bit or a lot. The density is what it is. It's going to melt at a certain temperature even if I have a little or a lot. But the volume is going to be different based on the amount that I have. So volume being 0.52 centimeters cubed is an extensive property. Now let's kind of look at taking our properties and dividing them into two other types of categories. We could divide it into physical properties or chemical properties. So this is two other ways we can divide things up. Physical properties are ones that you can see without changing what the molecules are. I can observe them is the way I like to think of it. So things like the odor, the taste, the color, the appearance, melting point, boiling point, and density. These are all things that I can test or measure or observe without causing an actual reaction to occur and without changing the chemical formula that I have. If you're describing what it looks like, right, that's really a physical property. A chemical property is basically when you're describing a reaction that could potentially happen. It might be corrosive, it might be acidic, it might be toxic. So you're kind of describing chemical reactions that could potentially happen. So look at these examples. These are all physical properties except one of them. One of them is not a physical property. It would be a chemical property. Answer choice D is a chemical property. If something is combustible, it means it has the potential to burn. Burning is a type of reaction. It's called a combustion reaction. It means that it's reacting with the air or with the oxygen that's in the air. Not everything is combustible. Not everything can go through a reaction with oxygen in the form of a combustion reaction. So it's describing whether or not a chemical change can happen. So that would not be a physical property. It would be a chemical property. So look at these ones. Which of the following is a chemical property? Squeezing oranges, melting some butter, separating sand out from gravel, hydrogen peroxide decomposing into water and oxygen, or ozone being a gas at room temperature. Only one of these is going to cause brand new chemicals to be formed. Only one of these takes the atoms and rearranges them to make brand new formulas. Choice D is the chemical property. The rest are not chemical properties. The rest are describing things you can physically do or describing physical changes that can happen, describing the appearance of something, a property. So D is the only one where a new molecule is being formed. We're going to make water and oxygen. Now let's look at the types of changes we can have, physical changes and chemical changes. And really the difference between the properties and the changes is kind of just a grammar issue. A property is something that could potentially happen. A change is something that is happening. So they're very similar. It's going to depend on how you phrase the sentence structure. Are you describing a potential situation, or are you describing something that is actually happening? Physical changes only change the state or the appearance. So maybe instead of a solid, it's now a liquid, or instead of a liquid, now it's a gas. Maybe you rip it, or shred it, or smash it, or break it. The atoms or molecules are not changing their formulas. It may look different. It may not be possible to put back together, but that does not mean the formulas, the molecules have changed. So for example, boiling water is a state change. We're going from liquid to gas, but it's still just water molecules. Down here, they're just closer together. They're moving slower. When they're a gas, they're further apart. They're moving faster. But you can see it's still an H2O molecule. So it is a physical change, boiling water. Chemical changes are what happen when we actually make something brand new. A brand new substance is going to be formed. I'm going to take those atoms, I'm going to break the bonds, I'm going to rearrange them, I'm going to make some brand new bonds into a brand new molecule or compound, and we're going to get a new substance. Sometimes it's very obvious that a chemical change has happened. Sometimes you can just look at it and tell. Sometimes it might be very, very slow and you don't know what's happening because you can't observe it. Sometimes it may be happening on such a small scale that you can't see it just with your eyes, but that doesn't mean it's not happening. So be a little bit careful with chemical changes because, just because you can't see it happening doesn't mean it's not happening on the molecular level. Rusting is a great example. The metal that's outside right now, the iron that's sitting out all over the place, is in the process of rusting. We don't always see it happening, right? Because our time frame is very, very slow for rusting. But it is happening. We have oxygen atoms that are bonding with the iron to make an iron oxide, which is a new formula. It has a new color. It has new properties. So a chemical change is like iron rusting. Real quick, one of the most commonly missed questions for chemical change is a question like eating your lunch. And that one's tricky because it depends on how you interpret it. If you're talking only about physically chewing something, that's a physical change. But when you chew something, you have saliva that gets released, and the saliva starts to break all the stuff down into different molecules. And so it kind of starts that process of digestion where you're breaking down the molecules into smaller and different ones. So chewing gets a little bit tough because, are you talking only about physically chewing? Are you talking about the saliva? Once you swallow the food and it goes into your stomach, all the stomach acid breaks it down, and that's also a chemical change. So it's a little bit tricky. I try to phrase questions in a way that will be more specific so that you know if I'm leaning towards just physical or if I'm leaning towards a chemical change. But you can always ask a clarifying question if you're not quite sure what the story of the problem is. All right, now let's classify matter into kind of some different ways. We know that matter is anything that occupies space and has mass. Usually we kind of classify it by the state that it's in. Is it a solid, liquid, or gas? Or what it's made of. Those are kind of the other ways that we kind of classify it, break it down, and describe it. The solid, liquid, gas one is pretty straightforward. The one about composition gets a little bit trickier because we have to know some key words here. So let's look at it by the composition or the components. That's another way to say it. So the first way we're going to kind of divide things up is by asking ourselves, is it a pure substance or is it a mixture? A pure substance is only one component, one type of molecule, or one type of atom. And it's going to stay the same. It's not going to change. A mixture, however, is when we have more than one. We're going to have two or more types of things mixed together. Pure substances can either be an element. An element's kind of as simple as it gets. It's like a single type of atom. You might have a lot of the atoms there, but you only have one type. One type of atom would be a pure element. You could also have a pure molecule. If all you have is hydrogen gas, Even though it's a molecule, it's the only type of molecule you have, so it's a pure substance. If all you have is pure water, pure H2O, it's one type of molecule, so it's a pure substance. When you get tap water out of the faucet, it is not a pure substance. There are minerals and all sorts of things in there. You are not just having pure H2O. In chemistry labs, we use what's called deionized water. We've taken all the minerals and all the ions and all the gunk out of the water so that we would have a pure water, pure H2O, only water molecules. Another word that you'll sometimes hear is compound. A compound is very similar to a molecule. The only thing that makes it different really is that it needs to have two or more types of elements. A molecule can be anything bonded, even like two hydrogens bonded or two bromines bonded. A compound is just a little more specific where we want to make sure that we have at least two types of elements. So hydrogen gas and bromine gas would not count. Yes, they're bonded. That makes it a molecule, but it's not two different types, so it's not a compound. All compounds are molecules, but not all molecules are compounds. It reminds me of kind of in geometry class, that rectangle and square situation, where all squares are rectangles, but not all rectangles are squares. One is a little bit more specific. A square is more specific. A compound is more specific. So now let's look at how we can divide up mixtures. We divided up our pure substances into these three things. Now let's divide up the mixtures. We're going to divide them into two categories. One is heterogeneous, where it's not very well mixed. It's not uniform. One part of the mixture will be different than another part. Some kind of classic real world examples are chicken noodle soup or oil and vinegar. Right, in your soup, every bite is not identical. In one bite, you might have a little bit of chicken. In another bite, you might have a carrot. Another bite, you might have a noodle, right? Not every piece is perfectly uniform. So that means it's heterogeneous. Oil and vinegar separate, right? The top will be different than the bottom. So that is heterogeneous. Homogeneous is when it is perfectly uniform. Things like salt water or the air, those are mixtures. Air is not pure oxygen. Air has all sorts of stuff in it. It has, nitrogen and carbon dioxide, water vapor. It has all sorts of stuff, but it's pretty uniformly mixed. One corner of your room doesn't have all the oxygen, and one corner all the nitrogen, and one corner all the water vapor. It doesn't work like that. It's well mixed. Sometimes people will mix up the concept of salt water and the ocean. Salt water is like a glass of water and you stir some salt into it and it dissolves. The ocean clearly is not homogeneous, right? The ocean is completely random mix of stuff. All parts of it are different from each other. So, when I say salt water, I mean like a glass of water that you stirred a little bit of salt into. Sometimes you might see on a milk carton, it might say homogenized. Milk naturally separates into a water layer and a fat layer. If you were to just get milk out of the cow, that would separate out. And you would have to shake it in order for it to mix back together before you drink it. And for the most part, people don't want to have to be shaking their milk up. And then, what if it's all clumpy and stuff? Like, that's weird. Nobody wants that. So what they do in the factory is they shake the milk so vigorously that the little fat droplets get so small that the mixture goes from a heterogeneous mixture into a homogeneous mixture. And they won't be able to separate anymore because it's now homogenized. So your milk started as a heterogeneous mixture and it was forced to become a homogeneous mixture. So if you look at your milk carton, you might see that word on your milk carton. So let's do an example. Which is heterogeneous? Kool-Aid, which is kind of like a punch if you don't know what Kool-Aid is. It's like a sugary powder that you mix into water to make like a punch to drink. Coffee, a latte, hydrogen peroxide, and ice. Only one of these is going to have distinct areas that are not the same. And it's going to be a latte. So if you're not a coffee drinker, if you don't know what a latte is, it's like a cup of coffee with milk in it, and then there's a layer of foamed milk on the top. So because the top has a foam layer and the bottom is just your liquid coffee and milk, it is heterogeneous. The top is different than the bottom. If you printed the glue-ins for your notes, you'll have a little chart like this that you can glue in. I like looking at this as a flow chart. I think it's helpful. We go from matter into pure substance or mixture. Mixture is either heterogeneous or homogeneous. Pure substances, either elements or compounds. This should really not say compound, by the way. This really should say molecule. One of the things you're going to notice all year long is that people are very, very sloppy with the difference between a molecule and a compound, which is unfortunate because they do mean different things. So even though this is technically wrong, I like putting this example up here because I do think it's a good option for you to write a little annotation in your notes to remind yourself, wait a second, it's a little bit a little bit wrong here. It should really be molecule, just so it kind of draws your attention. You're going to see all over the place, even in textbooks, they use molecule and compound interchangeably when they really shouldn't. If you did not print the glue in, you can go back at your own time and sketch it in later. I'm not going to sit here on the video and wait for you to sketch it. So either print a copy or go back and draw it on your own time. Okay, one of the things that sometimes we do in the lab is have to separate our mixtures. And sometimes that can be very easy and sometimes that can be really tricky depending on the type of mixture. We're going to be able to separate our mixtures because they're going to have different physical or chemical properties because they're different compounds, different molecules, different substances mixed together. And so we can essentially exploit those differences and use them to our advantage. So I like to just kind of go through some different types of separation techniques that you might come across so that when you do see them, you're not wondering like, why would I be using that technique? So kind of the most common is just decanting. You have a solid and you have a liquid and you're just kind of carefully pouring off the top layer of water. You're just trying to leave behind, in this example, the sand. In the lab, you maybe made a solid compound and you're just trying to get most of the water out. Not a very technical separation technique. It's pretty easy. You just kind of pour it off. Another one is called distillation. This is actually what we use at school in one of our prep rooms for the science building. We have a big contraption hooked up to a sink, and it uses distillation to purify our water. So what distillation does is it's going to take a liquid, you're going to heat it up and boil it. Whatever has the lowest boiling point is going to evaporate, or not evaporate, it's going to boil and vaporize first. Then it comes down a pipe where you have cold water running through on the outside of the glass. We call this a condenser. Sometimes they're straight like this. In the prep room where we have our sink, our distiller, we have a big coil system. But the main point here is that this is cold. So you're going to have the hot vapor coming into this cold column, and it will condense back down into a liquid. And then it's going to drip down into a new container. So what we do in our prep room is we boil the tap water. All the pure water vapor comes up, condenses, and I collect it in a big jug to use in our experiments. And down below, you leave all of the gunk that you don't want. So the idea here is that you heat it up. You're going to exploit the fact that things boil at different temperatures, and you're going to be able to essentially take out whatever boils first. Filtration is one that's very, very common. I would guess that you all know what it means to filter something, but you may not all know how to do a good technical filtration setup. There's some technique here to kind of get you the best results possible. Keep as much of your solid on your filter paper. We have really, really fancy filter paper at school that we use that can capture teeny, teeny, tiny particles. We have special fancy types of funnels that can like suck air down through them to help you dry it while you're filtering. We have all sorts of crazy like setups that we can do. But the main concept behind filtration is that you're going to use something like a piece of paper to trap any solid, and you're going to let all the liquid come down into a separate container. This is similar to decanting, but in decanting, you're trying to leave the solid behind. You're trying to leave it in your container. Whereas in filtering, you just dump it all into a funnel, and then you let it collect the solids up here. So a little bit similar, but it's a little bit better than decanting because you're going to be able to get your solid a little bit more dry, and you're going to be able to collect a lot more of the liquid. When you decant, you kind of leave a lot behind. This is a fun one. I think a lot of the middle schools do this. It's called chromatography. Chromatography is going to exploit the fact that some substances are attracted to certain types of liquid. And so we call that an intermolecular force when they're kind of attracted to each other. So if they're really, really attracted to the liquid and you have like a layer of ink here, it's going to pull different types of molecules up the paper as the water whips up the paper. So a lot of times like in middle school, they might do kind of like a crime lab where you have to decide who wrote a ransom note with which marker, and they would use chromatography to separate out the different colors, and you can see which pen wrote the note. That's kind of a classic middle school activity. And the idea there is that you can use the attraction between the molecules you're interested in and the liquid to kind of pull them apart for you. This was actually what my 7th grade science fair project was on, was chromatography. Kind of fun. Separating a compound or separating a molecule can be a lot harder. So usually you're going to have to use like fancier techniques. You can't physically separate them. Mixtures you can physically separate. Compounds you're going to have to chemically separate them. So for example, I can take a water molecule and I can rip it apart into hydrogen and oxygen. But I can't just like reach in there and yank on the molecules, right? Like I have to do something chemically. So one of the ways we can do that is to hook it up to an electrical source, and we can use electricity to rip the molecule apart for us. This is called electrolysis, where we're going to use electricity to do that for us because we can't really do that on our own. Here's kind of a picture of a real life setup. You can do this with a battery. Do not do this at home. This is not safe, okay? Don't do this. But in the lab, if you had proper safety equipment, we could set it up and you can actually see that you get twice as much hydrogen as you do oxygen because the water molecule has twice as much hydrogen as oxygen. So it's kind of a neat way that you can get an idea of like what the ratio is between compounds this way. You can like visually see it. So those are just some techniques that you might come across in a chemistry class that really are related to the concept of how do we classify these types of matter? Are they mixtures? Am I separating them based on their physical properties, physical changes? Are they compounds and I'm trying to separate them based on their chemical properties and their chemical reactions that we can do? So I hope that was helpful, and bye everybody.